Okay, so we're going to talk about chemical equations and again, balancing chemical equations here. And what we have up there is a balanced chemical equation. And when we do have any equations in chemistry, you always want to make sure that it is definitely balanced. And by balanced, what that means is that we have the exact same number of elements on each side of the arrow. And the idea behind that is, again, really the only thing that happens in a chemical reaction is we pretty much just break all the bonds and we kind of reassemble everybody on the other side of the arrow, if you will. And that really just involves electrons. So as we know, the thing that's most important in terms of what element it is the number of protons. So protons and neutrons, those guys that are in the nucleus, are really not involved in a normal chemical reaction. So since we're just really breaking electrons, we do have sort of like to call sort of the conservation of the elements. So if you started again with sort of 4 oxygens on the left, you should have 4 oxygens on the right. It should just be maybe in some different locations or different compounds. When we do balance the equation, we really do its coefficient, and that really is the thing that we should change when we balance the equation. And here we can see, for example, we would take the coefficient times the subscript, and that would give us like 4 hydrogens on the left, and we would do the same thing on this side, which would give us 4 hydrogens on the right. Much like most things in chemistry, if there's nothing written there, it is assumed to be a 1. So that basically would be 1 times 2, which would give us 2 oxygens. And once again, the coefficient in front of a formula will go for everybody that's behind it. So we would also take the 2 there and multiply it by the 1 for the oxygen, which would give us 2 oxygens. Now, in terms of sort of parts of an equation, the left-hand side of the arrow is really the starting material, and those are what are referred to as reactants. So those are the guys that are coming together basically to make what's on the right-hand side of the arrow, which are the products. And again, reactants always on the left, products always on the right. Some other things that we sometimes do see in formulas or equations, again, is the states of the compounds. And next to the formulas, you'll see S for solid, L for liquid, G for gas, and AQ is a very common one as well. And that means aqueous. And that basically means it's a water environment. It is basically a solution. So there is sort of a difference between something that is a liquid designation and something that is an aqueous designation. If something is a liquid, it is just a pure liquid by itself, which means it's really just one substance. So if you had just plain water by itself, that would be considered a pure liquid. Now, if you took something like water, and if you took some sodium chloride, which is salt basically, when we would put these together, the salt would dissolve in the water. And it would make basically a solution. You would be able to see the salt anymore, right? It would kind of dissolve into the water. And these two, when it comes together, will make a sodium chloride solution. And that guy would get the aqueous sort of indication there. So if it's a liquid, it really is just sort of one substance by itself, kind of a pure substance. If it's aqueous, it's basically made by mixing 2 things together. A lot of times water and something else dissolved in it will give you a solution. So most of the bottles that you use in the lab, those are really solutions, and water a lot of times is the solvent that's used there. So there's other things dissolved in there. Other things that we also sometimes will see again in the equation is on the arrow, a delta symbol there is used, or a triangle is used sometimes to represent heat. Also, a lot of times up on top of the arrow, we'll put something that's known as a catalyst. And a catalyst, once again, is something that is added to the reaction basically to speed it up, as in most cases. It's important to remember that a catalyst is not a reactant, it's not a product. It actually doesn't get used up in the reaction. It's really just there to facilitate that reaction occurring a lot quicker. So for example, you have a gas lab coming up, I think, from a handout. And when you do that one, there's actually a catalyst in there. And if you don't put enough catalyst, it's going to be a long night. Yeah. So you want to make sure you put enough of that catalyst into that reaction when you get to that lab, but it will speed it up. So these could be things like metals. So sometimes you'll see like PT written on top, like platinum metal or something like this. It could be like an acid, which is sometimes abbreviated with just like an H+ to represent like an acid is being used as a catalyst. Again, one last thing that you sometimes will also sometimes see up on the arrow is maybe water written. And usually what that means is you took something and pretty much kind of dissolved it in water. So kind of like our salt example there on the bottom, you took some sodium chloride solid and you kind of dissolved it in water and made like the sodium chloride solution. Any questions on any of that there? So when we balance equations, it's really important to, first off, make sure that they are balanced. And it's also really important that if you are ever given an equation, you should always take a moment to look at the equation and make sure that it actually is balanced, not just assume that it is. I would assume in most cases, if you see numbers in front of things, it's probably balanced unless somebody's trying to trick you. But if you definitely have an equation, there's like no numbers in the coefficient spot, you should definitely take a pretty good look at it to make sure that if it is balanced, it might be, but if it's not, you do need to balance it. So really, the couple of things that are really important. The first one there is really about a situation where you might be given everything kind of in words. So if you're given everything in words, like, you know, this reacts with this, and you're not really given formulas, it's really important when you write a chemical equation that you actually start with the correct formula. So that's like what we talked about with naming. You want to put everybody together in their proper formulas first. And then you want to kind of do the balancing part. So that's really important to get those right formulas down. Also, occasionally you may be asked to, like, you know, predict what comes on the other side of the arrow. That also is a situation where you want to make sure that you're starting with the correct formulas. Again, it's a very common mistake that people do is, as I might have mentioned, they try to sort of balance it and write the formulas at the same time. And usually what happens in those situations is they end up with the wrong formulas. They sit there all day trying to balance something that will never, ever balance because you don't have the right formulas. So always keep in mind, you want to get the right formulas and then do the balancing. Those things should be done in that order and not together. Otherwise, again, you'll probably end up messing up. Once you have sort of all the right formulas, we do balance by, as I mentioned, the only thing that we change is the coefficient. So only the numbers that come in front are the only things that we can change. As you hopefully know, we never change any of the subscripts because then it is no longer that substance if you change that. We don't, again, put any type of big numbers in between a formula, like in the middle. It always got to come in front of the formula. And as I mentioned earlier, any number that you do put in front does go for every element that is behind it. So it does get distributed to every element in the particular formula. So once again, if we put a 4 in front of water, it would count for the hydrogen, and it would also get distributed to the oxygen as well. So it does go to everybody that's behind there when you do put the number. Most people do a trial by error, but honestly, as I kind of said the other day, and as I'll do it here again, I personally like to make a table to sort of see what we're starting with in terms of the elements and how many we have in each side. And honestly, I personally like to go with what just seems like a pretty easy thing to kind of balance up front. Some people say you should start with the more complicated stuff, but you know, you can just look at it and go, you know, this is maybe what I need. And we basically will continue to put coefficients in until we basically have the same number of elements on each side. And usually what will happen is you put a coefficient on the left or maybe the right, and then you kind of go back and forth and you continue to put it in there until everything sort of falls into place is usually what should happen. At some point, you should have the exact same number of elements on each side. You want to double check that at the very end that you do. There's 2 things that you have to make sure of. First thing is all of the coefficients that you have, they all should be all whole numbers when you're all said and done. Set of whole numbers. So once again, if we kind of balance something like this, and we'll just say that that equation is balanced. But when we look at the coefficients, once again here, we could go through all these guys and basically divide them all down by 2 and still get whole numbers. And that means that the properly balanced equation in this example would be something like that. So it does sometimes happen that, you know, like I said, people can sometimes see maybe the bigger numbers to balance it, and it absolutely could be balanced with a certain set of coefficients. But if you can reduce down those coefficients to all whole numbers, you should do that, and that would represent really the properly balanced equation. In that case, any questions on that there? All right, so let us take a look at one here. So once again, if I were to approach this, I would make myself a table like reactant side, product side, and I would put in the elements that we got going on. So we got nitrogen, we got hydrogen, and we got oxygen. And again, I'll just sort of take an accounting of where we're starting with. So we got 1 nitrogen on the left. We have 2 nitrogens on the right. We have 1 oxygen on the left and 1 on the right. We got 2 hydrogens on the left and 2 on the right. So this just gives you a really good sort of place to start with. Gets you to visually sort of see, you know, where you might need to start or where you might want to start. And in this particular case, I could clearly see that everything is balanced except for the nitrogen, which seems like a really good place to start. So to fix the nitrogen on the left, again, we're going to put a coefficient in front of it, and that would be a 2 in this case. And that would get us 2 nitrogens. Again, that coefficient also goes for the oxygen. So that would give us 2 oxygens. And that will give us still 2 hydrogens. Pretty much this is always the case. You know, you go to fix one thing, and frankly, it screws up everything else. So now we just want to kind of look and see what might be the easiest thing to deal with at this point. So in this case, since the oxygen happens to be the only thing that is not balanced, we will go back to the other side and put a 2 there in front of where the oxygen would be. When I do that, that's going to give me 2 nitrogens. The 2 here would go to the oxygen, so that will give me 2 and basically 4 hydrogens. At this point, once again, we could clearly see that the hydrogen is now unbalanced on the left, and we could fix that by also putting a 2 in front of it. That gives us our 2 nitrogens, our 2 oxygens, and our 2 times 2, which is 4 hydrogens. So this would obviously represent the balanced equation. Any questions on that there? So let us take a look at another one here. Actually, we'll switch it up here. We'll change it. Let's do C8H18 plus O2, CO2 plus water. All right, so give that a go. See what you come up with here. I will too, since I just made it up, I guess. See how you're doing here. So once again, I'm going to start with a little table here. So reactant side, product side, I got carbon, hydrogen, and oxygen happening. Left-hand side, in terms of carbon, I got 8. Right-hand side, in terms of carbon, I got 1. Left-hand side, in terms of hydrogen, I got 18. Right-hand side, I got 2. Oxygen on the left is 2, and oxygen on the right is 3. 2 there and 1 there, right? Gives me 3. 3. Looks like quite a mess. All right, so we will start with maybe carbon. Seems pretty easy, right? To fix that, all I need to do is lay up an 8 here, I think. And if I lay up an 8 there, that's going to give me 8 carbons. Hydrogen will still be 2. And now my oxygen's up to how many? 17. 8 times 2 is 16, plus one more over here gives me 17. Yeah. All right. Now, hydrogen and oxygen are unbalanced, but in this case, I got oxygen and a couple of things on the right, and I got really just hydrogen and one thing on the right. So that seems a lot easier to fix first. So why don't we fix the hydrogen here? I got 18 on the left. I got 2 on the right. Is that a 9? Well, I want big numbers today. 9. Looks like a winner. That is going to give us 8 carbons. 9 times 2 is 18 hydrogens. Now my oxygens are up to, we got 16 happening there, right? We also have another 9 happening there. That's a lot. That's 25, I think they say. That is 25. Good so far? Yes. Okay. So clearly we don't want to do anything on the right-hand side there, I think, because we already put numbers, so that doesn't seem good. Our oxygen is really the only thing that we need to kind of fix on the left-hand side. So in this case, we kind of need to turn this 2 here into a 25, basically, to match it up there. So one way that we could do that is to use a fraction. So if we use a fraction like 25 over 2, when I take 25 over 2 times 2, which is essentially what I'm doing here, right? The 2's cancel and I end up with 25, yeah. And that gives me 25, gives me 18, and gives me 8 in this particular case. At this point, is this equation balanced? It is balanced in terms of numbers. Is it correctly balanced, though? It is not, because we cannot have what in our as our coefficient? Yeah, we can't have fractions. They need to be whole numbers. So you could definitely use a fraction like we did here to balance it, but you do need to get rid of the fraction. So to get rid of the fraction, I think they still call that a denominator. We multiply everybody in the equation by the denominator. So we're going to take this entire thing and times it by 2. And if we do that, that will give me 2 of the C8H18. That will give me 25 of the O2. That will give me 16 of the CO2, and that will give me 18 of the H2O. And if I did not screw up, this thing should still be balanced. So let's see. 2 times 8 is 16 carbons on the left, 16 carbons on the right. So that's good. 18 times 2 is a lot, 36, I think, hydrogens on the left. And 18 times 2 is a matching 36 hydrogens on the right. Oxygens, 25 times 2 is 50. I have 16 times 2 here, which gives me 32, and I have another 18 oxygens there. 18 and 32 is 50. Yeah. So it is balanced in this case. Any questions on that? Now, sometimes you do need to use a fraction to balance the equation, but you do need to clear it. A lot of times this happens when you have an element like we do here, oxygens and 2 separate things on one side, and you have like the elemental form of oxygen, O2 on the other side. So if you have like the elemental form of like a diatomic sort of element, and you got that guy in a couple of things, that's a lot of times where you might have to use a fraction to balance. By the way, the fraction is a very easy recipe as to how to choose the right fraction. The top number is the number you need. Okay, let's take a look, see how you're doing on these here. Pretty bad. Well, at least you're honest. Honesty is good. Really bad. Now I'm getting more depressed as I sit here. All right. I'm just going to go then. All right. So let's talk about a couple of things here. Let's talk about some approaches here that might not make it so bad for you. First off, if you were going to go element by element, which I'm not sure I would do on the first one, but if you're going to go element by element, just a reminder that when we do have something like with parentheses, you do have to distribute the guy on the outside right to each of those guys that are on the inside. And if you should have a number over here in front, that also would then get distributed to everybody as well. So again, when you do have parentheses, you kind of have to distribute in and then distribute out to the coefficient to make sure you get the right count for everybody. Now, if it was me and I look at this, I see some of our favorite things. Not really. But we do have some polyatomic ions happening here. We got a sulfate there. We got a sulfate there. A carbonate there. We got a carbonate there. And whenever you have an equation like this where you do have some polyatomic ions on both sides and they look exactly the same, sometimes it's a lot easier not to do element by element and sort of balance it as like polyatomic ion to polyatomic ion and kind of keep those guys together. So what I would do, for example, is you could start really with either one. It may work easier or not, depending on which one you pick. We'll give it a go here and see how we do. On the left-hand side, I have how many of these sulfates? 3. On the right-hand side, I have only 1, right? So to easily fix that, I need a 3 on the right-hand side, right, for my sulfate. When I put my 3 on the right-hand side, that does give me my 3 sulfates, right? But that also immediately changes my sodium to what? 6, and that's where I should go next. So now I got 6 sodiums on the right. How many do I have on the left? 2. So I need to put what on the left-hand side to get that to 6? Also a 3, yeah? So by putting that 3 there, that now gives me 6 sodiums on the left, 6 on the right. But the 3 that I put on the left doesn't just go for the sodium, it goes to the carbonate as well, which means I now have 3 carbonates on the left. How many carbonates do I have on the right? I have 3. Yes, I am done. Yes, don't unbalance it. Yeah, it's actually balanced. And that's what will happen in a case like that, is it will sort of all fall into place. You have your 2 irons. You have your 3 sulfates on both sides. You have your 6 sodiums on both sides. And you have your 3 carbonates on both sides. So if you do have some polyatomic ions working in an equation, it's a lot easier to kind of keep them together and just balance them as like whole units. And what will happen, just did there, we just had to actually throw full numbers in this case, and everything else really just fell into place. You can do it element by element, but when you have these polyatomic ions, it's definitely going to have a lot more. You got to kind of multiply in and multiply out. So there's probably a lot more room for error that could happen in that case. Sometimes just easier to keep everybody together. Any questions on that one there? Yeah. Now, the second one, we'd still actually polyatomic. So we could even try that approach here and see how it does. I got 2 nitrates there, right? And I got 1 nitrate on the right-hand side. So to fix the nitrate on the right-hand side, I should put what in front of it? 2. That's good. That gives me 2 nitrates on the left, 2 on the right. The 2 that I put in front of the nitrate on the right also goes for the potassium, which means my potassium now is 2. And that's where I should go to my left. And I need to do what to the guy on the left? Put a 2, yeah? That gives me now 2 potassiums on the left and also 2 iodides on the right or on the left, which matches the one on the right. And now I'm balanced, yeah? So again, you kind of work with those polyatomic ions, kind of keep them together. Everything really falls into place a lot quicker. Any questions on that there? All right, looking at our last one here. Again, if you want to go back, you can also do a table since we really don't have polyatomic ions here. So we could do a table. In this case, we have bromine, sodium, and iodide. And in this case, on the left-hand side, we have 2 BRs. Right-hand side, we have 1. Left-hand side, we have 1 sodium. Right-hand side, we have 1. Left-hand side, 1 iodide and 2 on the right-hand side here. So really, in this case, we have bromine that's not balanced, or we have iodine that's not balanced. You can start with either one, actually, in this case. It'll work out the same. I'm just going to start with bromine since it's the top of my list. So to fix the bromine on the right-hand side, I need to put a 2 there, right? That then gives me 2 of the BRs, gives me also 2 sodiums and 2 iodides. That means that I now need to go to the left-hand side and fix my sodium by putting a 2 there. That gives me now 2 of the Brs, gives me 2 sodiums. And once again, that also fixed my other guy here, gets me 2 iodines, and now I am balanced. Yes. Any questions on that there? So I would recommend polyatomic ions, kind of keep them together and balance them that way. If you don't have polyatomic ions, definitely do the table. It's kind of helpful to move you from one place to the next. Also keeps on track, hopefully, of, you know, getting everything balanced correctly. Any question on any of those 3 there? All right. So let's try one more here, I think. Let's try this one. And let's do one more after that too with this one. All right, balance these 2 here. So I'm gonna make a table on this one since I really don't have polyatomic ions kind of really happening on both sides or anything like that. So we got, in terms of our boron, 2 on the left and 1 on the right. Our oxygen is 4 on the left. We got 3 there, plus 1 more over there, makes 4. Our oxygen on the right, once again, we do need to distribute this guy into both of those. So that would give us a 3 for the oxygen. And our hydrogen here, we would have 2 on the left. And once again, distributing that 3 in gets us a 3 for the hydrogen. Again, at this point, you don't have a lot to work with on the right-hand side. So might as well just start with the first letter there, which is B. And we will put a 2 in front of it. That definitely should balance our boron to 2. Now, in terms of our oxygen, once again, we're going to take the 3 in, which gives us 3. Then we also need to multiply it by the number in the front. So that's basically 3 times 2, which would get us 6. Same thing will happen for our hydrogen. It's basically 3 times 1, which is 3, and then 3 times 2, which is 6 as well. Any questions on that there? All right, so clearly we're not going to touch anything on the right-hand side because, well, then that's just going to leave us here all day doing it. So we'll go to the left. Once again here, I got oxygen and a couple of things on the left. But in terms of hydrogen, I just have it in 1 on the left. So that's probably the easier of the 2 to fix. So we could fix the hydrogen on the left by adding a 3 in front of it. And that would get us 6 hydrogen. In terms of oxygen, we would have 3 here and another 3 here, which actually fixed our oxygen for us, which is nice. And that is a 2. So we are balanced at that point. Any questions on that there? So this is really what should happen as you're hopefully kind of seeing a pattern. At some point, things should just kind of fall into place as you put some numbers down. You might not have to put a number in front of every single thing you got there. You know, it should all kind of come together. Lastly, here, we'll do this one. I'll make my table up on top here. Reactions, products. We got some zinc. We got a little hydrogen and chlorine. Left-hand side, I got 1 zinc. Right-hand side, I got 1 zinc. Left-hand side, I got 1 hydrogen and 2. Chlorine on the left is 1, and chlorine on the right, excuse me, is 2 as well. So again, zinc is balanced. Hydrogen seems pretty easy to balance as well. We could put a 2 over here on the left-hand side. And when we do that, that leaves us 1 zinc. We now have 2 hydrogens because we put the 2 there. And that 2, once again, also goes for the chlorine. So now we have 2 chlorines. Dare I say I'm done? Yes, that would be balanced at that point. Yeah. So the other very common thing is people don't like to be done. Yes, they want to like keep putting numbers and taking numbers away and sitting there for 3 hours on the same balancing equation. You don't want to do any of those things, right? So don't unbalance something, by the way. Yes, if it's balanced, don't make it unbalanced by putting extra numbers in. Any question on balancing equations? Yes, we did a variety of different sort of samples, I think. All right, let us continue on then, I think. All right. So we're going to talk about types of reactions. And when we talk about types of reactions, there's actually several different ways that you could classify actually the same reaction. So a lot of reactions can be classified in many different ways, but overall, there's kind of two big classification of reactions. One big classification of reactions is redox reactions, which basically means oxidation, what we have here, oxidation and reduction reactions. And really the other big classification of reactions is what is known as double displacement reactions. So these are really two sort of big umbrellas for which you could more specifically classify reactions a more specific way, but they still fall under really one of these two sort of umbrellas. The reason for that is, frankly, there's really only three reasons why a reaction takes place. These are sometimes referred to as driving forces for a particular chemical reaction. The three reasons why a reaction takes place is the formation of a solid, which is sometimes referred to as a precipitate, PPT, the formation of water, and the third one is an electron transfer. These are really the three, boiled down to it, things that happen as to what makes a chemical reaction take place. The reason why these two guys here are really the big umbrella is a solid being formed and water being formed are pretty much what you get in a double displacement reaction, and electrons being transferred is basically what you get during a redox reaction. So those two classifications basically cover all the three reasons why a reaction actually takes place. And they all do boil down to one of those three things happening. Either electrons have been transferred, you made water, or you made a solid, pretty much. Now, some of those things you could see happen, and some of those things you might not be able to visually see. Frankly, when you make water, it doesn't look like much happened. You can't like visually see that you made water usually. But the other ones you could kind of see sometimes. You obviously see a solid being formed, electrons being transferred. You can't necessarily see the electrons being transferred, but you can see the end result of it. Maybe some solid sort of forms or some type of plating sort of occurs. So the first type of reactions we're going to talk about are redox reactions, which are these oxidation and reduction reactions. And this is pretty much the reaction that occurs when a metal and a non-metal gets together. If you remember when we talked about naming, a metal does what? It loses an electron, right? And the non-metal picks up the electron. That is an electron transfer. And that is basically what is happening when we make an ionic compound. When those two guys come together, you have the electrons being transferred, hence you have a reaction that's going to occur between the two elements, and you will make an ionic compound as a result of it. And there we go. That is sodium, which is a metal. And that is chlorine, which is a non-metal. And what's going to happen here, it is the sodium that's going to transfer its electron over to it. And let's talk a little bit about redox reactions and sort of the idea of oxidation and reduction, which are two types of reactions that we see a lot, and we see it also in organic chemistry when we get there. One definition of oxidation is something has lost electrons. The definition of reduction is the gaining of electrons. There are other definitions, like oxidation could also mean the gaining of oxygen as you go from reactants to products, or the losing of hydrogen as you go from reactants to products. And those we'll see when we talk about organic reactions. We look at like oxygen or hydrogen coming or going. Same thing with reduction. Sometimes people remember this as Leo the lion goes grr. That is the loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put them together, put Leo the Lion on the oil rig, and he goes grr. You don't have to choose. You could have all your memories here. But let's talk about really what happens with really what is referred to as oxidation state, but we could call it charge for our purposes here. When somebody loses electrons, do they become more positive or do they become more negative? They do become more positive, right? Because they have less electrons, more protons, right? So they become more positive. When somebody gains electrons, they become more negative. So a really simple way to determine is something going through oxidation or is something going through reduction is just like a basic number line. There's usually 0 somewhere. To the right of 0 are like positive numbers, right? To the left of 0 are negative numbers. So if you find the charge of your element on the left-hand side of the arrow to the right-hand side of the arrow is becoming more positive, like moving in that direction, it is going through oxidation. If you find your element on the left-hand side to the right-hand side is becoming more negative, like moving in this direction, it is going through reduction. And that's a very easy way to sort of just move your thing one way or the other, and you can basically figure out what's going on. So for example, if we look at this equation that we have going up here on top, if you remember, any element that is pretty much by itself, that's not combined with anything else, does not have a charge. So the sodium here does not have a charge. The chlorine, that's a diatomic molecule. That is how it naturally comes. It is uncombined. It does not have a charge. It is only when these two guys get together, right, that they actually form charges. The sodium here actually is a +1 charge, right? And the chlorine here, or chloride, is a -1 charge. Remember when we put a positive and negative guy together, an ionic compound, no charge overall, but it is still made up of two things that do have charges. So if I want to know which one is being oxidized, which one is being reduced, I frankly could just pick one element. So we will pick the sodium, for example. And my sodium is starting at 0, which would be like here, right? And on the right-hand side, it ended up at +1, which would be going in that direction. Yes, that means the sodium is doing what? It is being oxidized or going through oxidation. By the way, the beauty of oxidation and reduction is they always happen together. So if somebody gets oxidized, somebody else gets reduced, which means by default, the Cl is going to be reduced. And you can verify that by looking at the same thing. The Cl started at 0, right? On the left-hand side, which would be like here, and it ended on the right-hand side at -1, which would be going in that direction, and it is now being reduced. So you could choose either one if you want to determine, and actually once you determine one, the other guy is doing the opposite things because they always occur together. So in this particular case, it is the sodium that's being oxidized, which means it's giving away its electrons. And it is the chlorine here just saying thank you very much and picking up its electrons, and that makes our ionic compound here. This overall is a redox reaction because we have the electrons being transferred here. So it falls under the big umbrella of a redox reaction. We will later talk about it here, but this also can be classified as a combination reaction, or a synthesis reaction, which is the same thing, because it's basically two things that make one thing, but it's still a overall redox reaction that's happening. But if you want to get more specific, you could specifically classify this as a combination or a reduction reaction. I'm sorry, combination or synthesis reaction. So this is an oxidation reduction reaction. We could look here at another example. This is magnesium, which has no charge here. This is oxygen in its natural state, has no charge. When magnesium and oxygen get together, what charge does magnesium take? Magnesium's group 2, which means it has +2. Oxygen's group 6, which means it has -2. I was going to write -6, but it felt wrong. But it is -2 there. So once again, if you're not sure, we could follow what's happening. If we look at the magnesium and blank the screen, if we look at the magnesium, it is starting at 0, right? And it's ending where? at +2 on the other side, which means it's moving to the right. It's becoming more positive. That means magnesium here is going through oxidation or reduction. Oxidation. Yeah. We could again do it for the oxygen if you want on the left. The oxygen starting at 0, and on the right-hand side, it ends at -2, which would be going in this direction, becoming more negative, which means the oxygen here is going through reduction, basically. Yeah. Any questions on that? So what's really happening here is the magnesium is going to give away a couple of electrons here, which actually will be 4 total electrons. And this is what is sometimes referred to as the oxidation half reaction. And that is because electrons are on the product side, like they are being given off. It is 4 electrons because each magnesium loses 2, right? And there's 2 of them, so that gives you 4 electrons total, basically. Basically, the oxygen there says, thank you very much for the 4 electrons. I will take those and I will make this guy here. And this is what is sometimes referred to as the reduction half reaction. And basically here we have 4 electrons. Each oxygen gains 2 of them, which is why they each have a -2 charge. And it's a perfect transfer of electrons. However many electrons the guy that's being oxidized loses is the exact amount of electrons that the guy that's being reduced will gain. So it's a perfect transfer of electrons from one place to the next. And they should always be the same number of electrons that it moves from one guy to the next. Any questions on that there? Yeah. So we'll talk a little bit more about this when we get to organic chemistry, but sometimes in organic chemistry, we don't have a lot of metals happening. So a lot of times it's easier to look at the other sort of definition of oxidation and reduction. Another definition of oxidation is something gains oxygen from left to right and something loses hydrogen. So there's really 3 definitions for oxidation. It is the loss of electrons, the gaining of oxygen from reactants to products, and the loss of hydrogen as you go from reactants to products. And reduction is basically the opposite of those definitions. So reduction has 3 definitions. It is the gaining of electrons. It is the loss of oxygen as you go from reactants to products. And it is the gaining of hydrogen as you go from reactants to products. Once again, organic chemistry will see a lot of these 2 definitions here, looking at hydrogen and oxygen. But really for sort of inorganic chemistry, like in this chapter and stuff like that, we could really look at loss and gaining of electrons as sort of the main thing. But later on, when we get into organic reactions, we'll look at those other definitions. So just to quickly look at the other definitions here. For example, this is sulfur, and as sulfur goes from the left to the right, it actually will gain some electrons, right? Gain some oxygen, which means it is going to go through oxidation. Our oxygen actually disappears. The copper over here has oxygen on the left, loses oxygen on the right, which means that it is going to be reduced in this case, the copper on this side. So this guy would be reduced. This guy would be oxidized because of that. And same thing here. This guy actually gained oxygen, which would mean it would be oxidized. This guy would be reduced. So sometimes there's no metals or anything involved. It's a little bit easier to sort of figure out what's going on. By the way, the bottom one does have a metal, which means that's all you could focus in on if you wanted to. The charge on the copper here on this one is what? +2. That's because the oxygen here is -2, right? On the right-hand side, that's copper by itself, which means it has no charge. Any element by itself basically has no charge. So if you weren't sure, you could look at the copper in this case and see that it started at +2, which would be over here, right? And ended at 0, which means it is moving in this direction. That means the copper is going through reduction, like we found with the other definition there. So you could do that, and then hydrogen would go through oxidation. So if you do have a metal, just following the charge on it is really an easy way to identify what is happening. So for this chapter, obviously, we'll focus in more on the gaining and losing of electrons. And again, we'll revisit the other definitions when we get to sort of organic there. Any questions on that there? So that's hydrogen, which we talked about. All right, so let's talk about classifying these reactions. As I mentioned, there really is these three driving forces for why reactions take place. Solid being formed, which once again is sometimes referred to as a precipitate. Water being formed, which is the formation of H2O. And again, our electrons being transferred is also the third reason why it happens. So the first type of classification, which is referred to as a synthesis or combination reaction, is basically what happens when you take basically two things make one thing. Basically, you put them together, you combo them together, hence the name combination or synthesis reaction. So right here, this is two things make one thing. That's your classic synthesis or combination. This guy here is two things that make one thing, also your classic combination or synthesis. Both of these things are also redox reactions. They're actually transferring electrons. The hydrogen here is 0. The oxygen here is 0. The hydrogen here is +1. And the oxygen is -2. So if we look at what is happening there with our hydrogen, it is going from 0 to +1, which means the hydrogen here is being oxidized. It is becoming more positive. The oxygen is going from 0 to -2. It's becoming more negative, which means this guy is going through reduction. So as I mentioned before, the big classification of what's really happening here is a redox reaction. A more specific classification of what's happening here is a combination or synthesis reaction. Two things make one thing. Obviously, this is also a redox one we did earlier. 0, 0, +1, +1, and -1. So a more specific classification, synthesis or combination. A more sort of broader umbrella classification would be a redox reaction. The next sort of type of reaction is basically the opposite of a combination or synthesis reaction. It is a decomposition reaction. So in synthesis or combination, you take two things, make one thing, put it together. In a decomposition, you basically take one thing and you break it apart. So it's basically the opposite sort of reaction that takes place. You start with like one thing and you make multiple things. So as we can see here, if you run an electrical current through water, one thing makes multiple things. That is a decomposition reaction. This is mercury 2 oxide. One thing makes some mercury liquid and some oxygen. One thing makes two things. Again, these are decomposition reactions. Basically the opposite of combination. So combination, put it together, decomposition, break it apart. These once again are also these type of reactions here. Also fall under the big category of redox reactions. Once again, you got this guy that's +2, for example. That guy's -2. That is 0 and 0. So if we look at the mercury in this case, what's happening with the mercury is starting at +2, which would be over there, and it's ending at 0, which means it's becoming more negative, right? So in this case, if you become more negative, it is actually going through reduction. Yeah. The oxygen starts at -2 on the left and ends at 0, which means it's becoming more positive, which means the oxygen here is actually going through, if I could write it there, maybe come back, oxidation. Yeah. So once again, a decomposition reaction is a more specific classification of a bigger reaction that's basically still a redox reaction that's happening. So to sort of specify what's sort of happening here, you specifically call it a decomposition reaction, which basically means one thing breaks apart into multiple things. Any questions on that there? The next type of reaction is a single replacement reaction or single displacement reaction. I think most people these days call it a single replacement reaction. So a single replacement reaction has this general formula. A plus BC goes to B plus AC. This can be a metal. And this is an ionic compound. So this is a positive and negative guy. And if this was a metal, it does not have a charge here. It will come in and replace the positive guy. And when it does, it will make a new ionic compound. And the guy that it replaced will come out with no charge. It's sort of its elemental form. It'll just kind of come out by itself, uncombined in that situation. You could also do this with a non-metal. This is a positive negative guy, and this is a non-metal. And non-metals do not have a charge to begin with, but when they do get a charge, they get a negative charge. So it'll come in and kick out the negative guy in this case. We'll make a new ionic compound. And again, that negative guy will come out by itself with no charge. So that's exactly what has happened here with this equation that we balanced earlier. We have our zinc plus our HCl goes to our H2 and our zinc chloride. When zinc comes in, this is hydrochloric acid. It is a positive negative guy, and this is something that has no charge. So the zinc will come in and kick out the hydrogen. When hydrogen comes out by itself, it makes hydrogen gas. You should see bubbles. Yeah, so you'll start to see bubbles happening when you do this. And that is the hydrogen gas being formed. It will make this new ionic compound over here, which is a positive and negative guy. In order for this reaction to actually take place, whatever that is coming in needs to be more reactive than what it's replacing. So if you did this reaction, which you probably did, I'm assuming maybe, if you did this reaction and you saw it actually take place, that means that zinc would be more reactive than hydrogen. So whatever is coming in needs to be more reactive than is what is replacing for this reaction to take place. For example, if you did this same reaction, but used to use copper plus some hydrochloric acid, the copper, when it would come in, is less reactive than the hydrogen. You would get no reaction would occur. And you would know then that the copper in that case would actually be less reactive than the hydrogen because the reaction didn't take place. Now, this is a single replacement reaction. Basically, something by itself, either a metal or non-metal, not combined with anything, plus something that's ionic, a positive, negative guy. That is the classic setup for a single replacement reaction. This is also still, we can't get away from it. This is still a redox reaction that's taking place. This zinc has no charge. This is +1, that is -1. Hydrogen by itself has no charge. This is +2 and -1. So if we just look at, for example, the zinc. The zinc is starting at 0, which would be here, and it's ending at +2, which means the zinc is becoming more positive. And that means that the zinc is going through oxidation. Yeah. It is actually the hydrogen here that is going through reduction. The hydrogen is starting at +1 and ending at 0. It's becoming more negative. How about the chloride? What is it doing? Is it changing? Chloride on the left is -1. Chloride on the right is -1. Did it change? It did not. It's what's referred to as a spectator ion. It's just there for the ride. Yeah, it's just watching what's going on. It's there to balance out the charges. So the thing that's actually being oxidized again is the zinc in this case, and it's the hydrogen being reduced. The chloride is just simply there to balance out the charge, not really participating. So again, this can be a redox reaction under sort of the big classification. Most people will use a more specific classification of this is a single replacement reaction. Any questions on that there? All right. So another type of reaction is a precipitation reaction, which does fall under the double displacement reaction category. So remember that double displacement is another big category. And in a double displacement reaction, it has this general formula, AB plus CD. And what both of these guys are ionic compounds. So you basically have two ionic compounds, two guys with charges. And what always happens in a double displacement reaction is the two positive guys will switch partners. And that means that the A, which is positive, will hook up with the D that's negative, and the C that was positive will hook up with the B that's negative, and it will make two new ionic compounds on the right-hand side. Now, one of these combinations may result in an actual solid being formed, and if a solid is formed, that means that we can more specifically classify this as a precipitation reaction. So a precipitation reaction is a more specific classification of a double displacement reaction. And if we look at what is going on here, that is exactly what is going on. We have our potassium that ends up switching partners with the nitrate on this side. And we have our positive barium that ends up hooking up with the chromate on that side. And basically our two positive guys switch partners, basically is what happens, making two new ionic compounds. And in this particular case, one of those guys does make a solid. So that is why it's referred to also as a precipitation reaction, because we made a solid, but it's also oftentimes classified as a double displacement reaction because the two positive ions basically swap places. This reaction here is not a redox reaction. There is absolutely no electrons being transferred. This would never be classified as a redox reaction because the potassium on the left is +1, so is the potassium on the right. The chromate is -2 on the left, so is the guy on the right. So there is no electrons being transferred here. There is no redox. Double displacement is its own sort of category of reactions. Any questions on that there? So once again, here we have that double displacement reaction that occurs. We're switching partners. The two positive guys do that, and we get that solid that's formed, which again is considered a precipitate and a double displacement. Now, this is an acid-base reaction. It's sometimes referred to as an acid-base neutralization reaction. And that is because whenever we take an acid like this guy, which is hydrochloric acid, plus a base like this guy, which is potassium hydroxide, we always form two things. We always form water and a salt. And a salt is a fancy word for an ionic compound. And this is called a neutralization reaction because really what is happening here is the formation of water. So if you remember, that is one of the reasons why a reaction takes place. We actually just formed water here. This type of reaction also falls under the double displacement banner, if you will, because this is a positive guy, that's a negative guy, that's a positive guy, that's a negative guy. And basically what happens is our positive guy here goes over and hooks up with the negative guy there. When you have an H and an OH, what does that make? That is where the water comes from. Yeah. So that is where the water actually comes from. And that's really the actual reaction that's happening, is those two things coming together. The salt comes from the other two things. The positive potassium goes and finds the other guy, which is the negative chloride. And we get this guy, which is our salt. So this is definitely a double displacement reaction. It can more specifically be classified as an acid-base reaction. Again, here, this is not a redox reaction. There is no electrons being transferred, but it does fall under that double displacement banner. Again, that double displacement banner is where we get precipitation reactions and water being formed, which again is two of the three reasons why a reaction takes place. Any questions on that there? Now, the last sort of classification of a reaction is a combustion reaction. And I'll be honest with you, most people, when we think about a combustion reaction, think about this organic combustion reaction, like when you light the Bunsen burner. And in an organic combustion reaction, you have an organic compound like this guy. And an organic compound is like a carbon, hydrogen, oxygen containing guy. You always have O2 on the left-hand side. And in this type of combustion reaction, those are always the products that you form. CO2 and water is typically the products that you form in an organic combustion reaction. I will say that there is, frankly, a basic general definition of combustion, which is very, very general. And it pretty much says, if you have a reaction and you got O2 on the left-hand side, it's a combustion reaction. So anything with O2 on the left-hand side there by itself is a combustion reaction, which means the one that we saw earlier, for example, the magnesium plus the O2 that made the MgO. This was a redox reaction, if you remember, right? Because we had the electrons transferring. 0, 0, +2, -2. This is also two things that make one thing, right? Which means you could classify this as a synthesis reaction, right? Or combination. And it also has oxygen, which means you could classify this technically as a combustion reaction. So as you can maybe see here, there are multiple ways that you could classify the exact same reaction, depending on sort of what you're looking for. And this particular one, you could classify three different ways, depending on sort of what you are looking at. Do they let you do this reaction? Like you burn the magnesium, you're supposed to observe what happens, but not look at it? No? Oh, it's my favorite one. It's like they tell you in the instructions, observe what happens, but don't look at it as it's burning. It's very, very bright, like a firework, so you get blinded if you actually look at it. So just to summarize real quick before everybody runs out. I felt the running. All right. So under redox reactions, which is the big umbrella of electrons being transferred, you could more specifically classify reactions as a synthesis reaction falls under that. Also, the combination, which is the same thing. Decomposition falls under that. Single replacement reactions fall under that umbrella. And combustion reactions all fall under basically the redox reaction. It's basically electrons being transferred. That's essentially what's happening. Under the double displacement reactions, where we have the two positive guys switching partners, you can more specifically classify a double displacement reaction as a precipitation reaction, where you make a solid, or an acid-base reaction where you make water. So once again, you basically make water there. Here you make a precipitate, and over here you have electrons being transferred, and that accounts for pretty much all the reasons why reactions take place and all the different combinations of really where they fall under. Any questions on any of that stuff there? All right, well, it's good to see you.